In the last video, you got started with asynchronous Node.js development, and even with a simple script like this one, we ended up asking a lot of questions and not getting a lot of answers. The goal of this video is to explore the internals of Node and V8 to see how asynchronous scripts actually execute. That's going to give us answers to questions like, why does this 2-second set timeout delay not prevent the rest of the program from running? And why does a 0-second delay cause this function to run and print 0-second timer after stopping prints, which is exactly what we're seeing down below. So the goal is to explore the internals to get a better understanding of what exactly is happening. I actually recommend watching this video twice. Watch it once right now, then watch it once we're done building the weather application, and you have a lot more exposure to various forms of asynchronous programming. That's going to really reinforce and reinstill exactly what's happening behind the scenes. Now, we're going to start off with a little visualization working through how Node would execute a synchronous example. Then we'll explore exactly how Node would execute this script line by line. I'm excited to get to that, and so let's jump right in. Right here, we have our first of 3 examples. Now, even for a simple synchronous example like this one, there is still quite a bit going on. So let's take a quick moment to break down what we're seeing here. At the top left, we have the Node file that's executing. So this is our very simple script. We create a couple of variables and we print a message to the screen. Down below, we have the terminal output for that script. So as the script prints something, that'll show up down here. On the right-hand side, we have all of the internals that are running behind the scenes in both Node and V8. We have our call stack. We have the Node APIs, our callback queue, and our event loop, all of which work in tandem to get our asynchronous programs running. Now, for simple synchronous examples like this one, the only of these 4 we need to worry about is the call stack, so let's take a moment to start there. The call stack is a simple data structure provided by the V8 JavaScript engine. The job of the call stack is to track the execution of our program, and it does that by keeping track of all of the functions that are currently running. Now, you've actually seen a call stack before. If you remember, in the last section, we debugged an error message that we intentionally created in our program, and we saw 2 things. We saw the actual error message, and below that, we saw a long list of all of the functions that were running to get to that point in the program. That is a call stack. Now, the data structure for the call stack could not be simpler. You can add something onto the top of the list and you can remove the top item. That is it. So think of it like a can of tennis balls. Not that I've ever played tennis. You can add a tennis ball onto the top by dropping it into the can. And if you want to remove one, you have to remove the top one. I couldn't remove one in the middle without first removing the ones above it. And I couldn't add something to the bottom of the list if there were already things inside. So let's go ahead and see how the call stack is going to help us execute our simple program on the left-hand side. The first thing that's going to happen is that our script, it's going to get wrapped in that main function that Node.js provides. In the last section, when you debugged your Node.js applications using Chrome, you saw that you had your application code showing up in the Chrome browser, but we also saw that our code was wrapped inside of a function that we did not create. That function was defined by Node, and while it's an anonymous function, it's often referred to as the main function for the program. So what's the first thing that happens? The main function gets pushed onto the call stack, dropping all the way to the bottom since there's nothing else inside. Now, when something gets added onto the call stack, that means it's going to get executed. So we're going to kick things off up here with line 1. We create a constant. We create a constant x with the value of 1. Then we go ahead and create the constant y, the value x plus 2, which would be 1 plus 2, which is 3. And then we move on to log the sum is followed by the sum, which in this case would be sum is 3. Now, log is indeed a function. And remember, whenever we call a function, the function gets added onto the call stack. So right here, we're going to drop a call to log onto the call stack. So we have main and we have log. Now, once log is dropped on, that's actually going to run and we are going to see our log show up. So in the console, we would get sum is 3 printing, and that's exactly what we would see if we ran the program. Now, when a function finishes by either running to the end or returning a value, it gets removed from the call stack since it's no longer executing. So at this point, log has done its job. It printed something to the console. It's now going to finish by getting removed from the call stack. Here, our little blue arrow would go on to the next line of the program, which is actually the end of the script, which means our main function is going to finish as well. That's going to get popped off the call stack, and we are left with an empty call stack. At this point, the program is done. Now, this is just the first basic example to get comfortable with how the call stack is going to work. The next example is still a synchronous example, but there's a bit more complexity with multiple function calls. If we take a brief look at the script, I can see I define a list locations function. It takes in an array, and for each location, it loops through it, printing it to the console. Down below, I define the locations and I pass them into the function. Let's see exactly how things would run should we run this script. So once again, the first thing that happens is the main function gets pushed onto the call stack that allows the script to start executing. Right here on line 1, we define the list locations variable, creating the function, which is the variable's value. Now at this point, we are not calling the function, so it's not going to appear on the call stack. The next thing that happens is we move on to line 7, and this is where we define our myLocations array, adding a couple of locations in. From there, we move on to line 9, and that's where we call list locations with the array of locations. Now this is indeed a function call, so we're going to see list locations added onto the call stack. It's going to get pushed onto the stack. Now it's the top item, and I've just summarized the argument value so it all fits in this nice purple block. So from there, list locations is actually going to start running. That's the function that's defined here and ends down below. Now the only thing inside of this function is a call to the for each method. We're looping over each location provided. So for each, that is indeed a function call, it's also going to get added onto the call stack, and I have ... in place of its true argument, which is the function to run. This function is going to run one time for each location. It gets access to the individual location, and it prints it. So that's the next thing that's going to happen in the program. For each is going to be responsible for calling this function multiple times. And the first time it gets called, it does indeed get added onto the stack. So right here, what happens? We see that the anonymous function is called with the argument Philly. And then from there, we actually call console.log, another function, so that gets added onto the stack as well. Now console.log, once again, is indeed going to print something, so we'll see that appear down below. Now console.log is going to finish, so that's going to get popped off the stack. And once console.log is finished, our little anonymous function, which starts here and ends here, that's also going to finish, since console.log was the only statement inside of there. So that goes ahead and gets popped off the stack as well. Now, for each doesn't get popped off the stack because it's not quite done yet. It still has to call the anonymous function again to make sure that New York City prints. So we are going to see a new anonymous function added onto the call stack, and then from there, we're going to see another console.log call, this time printing NYC. That's going to show up down below. And then from there, we will indeed pop off the console.log call and the anonymous function call. Now at this point, for each has gone through that process 2 times. There are only 2 items in the array, so for each is done, and that's going to get popped off the call stack as well. Now that for each is done, list locations is also done, as that's the only thing that list locations does. It just calls for each. When for each is done, the function's over. So right here, that gets popped off the stack. Now that brings us back to where we were before on line 9 of the main function. That is the last line in the program, which means that we are all done. The final result, we have Philly printing, and then below we have NYC printing. So here we were able to get an idea for how the call stack is going to allow us to work through our program, keeping track of the individual functions that are actually executing. Now let's go ahead and move on to the third and final example. This is our asynchronous example that we actually wrote out and ran in the last video, and we're going to explore how it ran behind the scenes, so we can figure out why we were seeing things in the order we were seeing them. Now for this one, since it is asynchronous, we will be using the call stack along with Node APIs, the callback queue, and the event loop, all working together to get our application running. Now, like with our other synchronous examples, the first thing that happens is that main gets added onto the V8 call stack that starts the execution of our program. We start on line 1 with a call to log. We've already seen what happens when we do that. Log gets added onto the call stack, our message shows up over here, and then log gets removed as the function completes. Next up, as you might have expected, we move on to line 3. That is a call to set timeout. Set timeout is clearly a function, so something new gets pushed onto the call stack. Now, set timeout is not a part of the JavaScript programming language. You're not going to find its definition anywhere in the JavaScript spec, and V8 has no implementation for it. Instead, it is Node.js, which creates an implementation of set timeout using C++ and provides it to your Node.js scripts to use. As we saw, it is an asynchronous way to wait a specific amount of time and then have a function run. So when we call set timeout, it's really registering an event with Node.js APIs, and that is an event callback pair, where the event in this case is simply to wait 2 seconds, and the callback is the function to run. Another event callback pair might be to wait for a database request to complete, then run the callback that does something with the data. So right here, when we call set timeout, a new event gets registered in Node APIs. Here we have our set timeout callback, and we're waiting for 2 seconds. Now at this point in the process, that 2-second clock starts ticking down. While we're waiting for those 2 seconds to happen, we can actually do other stuff inside of the call stack. So JavaScript itself is a single-threaded programming language. You can do one thing at a time, and the call stack enforces that. We can only have one function on the top of the call stack. That is the thing we're doing. There's no way to execute 2 things at the same time. Now, that doesn't mean Node.js is completely single-threaded. The code you run is indeed still single-threaded, but Node uses other threads in C++ behind the scenes to manage your events. That's what allows us to continue running our application while we're waiting those 2 seconds. We don't have to completely wait, and this is the non-blocking nature of Node. This is not blocking the rest of the app from running. So from here, what do? We move on to another set timeout call. We go on to line 7. We call set timeout again. This is going to register yet another event in the Node APIs area, a callback, where the event is 0 seconds. And at that point, we now have 2 Node APIs waiting in the background. So we can still continue to do other things while both of those are waiting for the event to complete. In the first case, 2 seconds. In the second case, 0. Now, where do we go from here? Well, these 0 seconds are up. So this callback needs to get executed. Now, how exactly does that happen? Well, this is where the callback queue and the event loop down below come into play. The job of the callback queue is simple. Its job is to maintain a list of all of the callback functions that are ready to get executed. So when a given event is done, in this case, when the 0-second timer is complete, that callback function, the function we defined right here, that's going to get added onto the callback queue, which is just a standard line. You get in at the end of the line and you work your way towards the front. The front item is the one that will get executed first. So right here, since there are no items in the list, the callback gets added right up front. So we have this callback and it's ready to get executed, but before it can be executed, it needs to be added onto the call stack. That's where functions go to run. Now this is where the event loop comes into play. The event loop looks at 2 things. It looks at the call stack and it looks at the callback queue. If the call stack is empty, it's going to run items from the callback queue. So at this point, the event loop says, I know you got added to the callback queue, but the call stack is not empty, so I can't execute you, and this is why our function doesn't run right away. The event loop needs to wait for the call stack to be empty, so at this point, main actually continues to run. The next thing we see is that line 11 of our program is going to run. That is a call to log, so the function gets added onto the call stack. Our message prints down below. The function gets popped off the call stack, and at this point, the main function is done. So from here, main gets removed. Now with our regular synchronous scripts, this is when the program actually finished. The end of main signified the end of the application. That is not the case with our asynchronous programs. Right now, the event loop can start to do its job. It can see that the call stack is empty, and it can say, okay, do I have anything in the callback queue? I do. So it takes that item and it moves it up to the call stack so the callback can run. So at this point, our callback function is running. That is going to execute the function right here. There's a single line inside of there. It is a call to log. That gets added onto the call stack. Our message prints, printing 0 seconds. It gets removed, and then the callback function is done. So this is why we were seeing 0 seconds after finishing up. None of our asynchronous callbacks are ever going to run before the main function is done. So at this point, the program still isn't done. The call stack is empty. The callback queue is empty, which means the event loop can't do anything. The program just sits there for 2 seconds. At that point, our other event is done. Its callback gets pushed onto the callback queue. The event loop detects that. It notices the call stack is empty, which means it's ready to run. It takes that callback, bringing it up to the call stack, and it executes it. So that is defined on line 4. We have our call to log. We get our message to print, printing 2 seconds. That gets removed. The callback gets removed. And at this point, the program is complete. The call stack is empty, the callback queue is empty, and there are no other events registered with Node's APIs. This means the process would be complete, and over here we have the exact same output we got when we actually ran the application. The only difference is that we now know why we got the messages printing in the order we saw them. Because Node uses other threads behind the scenes for those Node APIs, we could see why Node is non-blocking, allowing finishing up to print even though we're waiting 2 seconds for our other message to print. We also learned why we were seeing finishing up print before 0 seconds. That's because the event loop can't run any of our asynchronous callbacks until the call stack is empty, which means that main needs to finish first. If you have any questions about what was covered here, just crack open a question in the Q&A. And remember, this is not the end of our discussion on asynchronous programming. This is just the beginning. The goal here was to give us a mental model of what's happening. Now we're going to dive into the rest of this section and actually explore how we can get real data from HTTP APIs into our application. I'm excited to get to that, so let's go ahead and jump right in to the next video.